Hi, everyone. Thanks for joining. I'm going to start the slideshow now. All right, so I'm calling this Pythagorean metal. It takes from the golden spirals that have been known for a long time, and then also Vera de Spinedale's addition to it, and then adds another addition using Pythagoras' theorem. Vera de Spinedale's addition is called the metallic mean family. So here's the golden spiral. There's quite a bit about it on Wikipedia, but in case you don't know, it's related to the Fibonacci numbers. The Fibonacci numbers can approximate it as they grow in size, closer and closer. And then it's been used in quite a bit of architecture. Notably, Brunelleschi experimented with it, and he's the visual artist who figured out perspective drawing, and he helped with Frenze Domo. Golden spiral has been attributed to quite a bit that it doesn't actually apply to, but it also has applied to a lot. So. And then here are the metallic means. So the very first metallic mean, golden spiral here, everyone's familiar with, but then the next ones people are less familiar with. Silver here is probably the second most common. A4 paper uses it. So when you fold A4 paper, it's self-similar. And also Japanese architecture uses that. So European architecture is more into the golden spiral, and Japanese is more into silver. And then the other ones, though, bronze and all that, they're not so well known. Getting into the mathematics of it, all of these metallic means are very interesting because they're continuing fractions just with the n change. So if n is 1, it's the golden ratio. If n is 2, it's the silver ratio, 3, bronze. And so it's just an index. And then down at the bottom here is the closed form formula for the metallic means. Here's Vera, the person who invented the metallic means. She was a polymath who was also an architect. That was her main trade, as well as mathematics. There's a write-up about her on Wikipedia, and she also has something she published about the metallic means here. She did have a website, Vera's Mathematical World, but last time I checked this morning, it wasn't working. So hopefully it will come back online, but she is someone I think that we should celebrate much more. So hopefully we can get the word out who she was. She definitely inspired my work. And then, yeah, so what I did to extend her work. So after quite a bit of playing around and experimenting, I figured out that the hypotenuse here, if it's moved onto the vertical line, then it can describe the border for these types of spirals. So instead of using this formula here for closed form, which only works for the metallic means, we can use it for any type of right triangle as a seed, using a squared plus b squared equals c squared. And then just have the c minus b. So here's 1b right here, and this b is a 5 length. And then here's the c. So this whole thing is c plus b. Yeah, so c minus b gets us, c minus b, so b's right here as well. So 2b, that's kind of the trick with this stuff. I'm kind of getting the math, and we can do that if we want, but I'm actually going to back up now because let's just stay on the art level. And there's another way to describe it here, which is taking this length and comparing it to this and that length. And in our discussion, yeah, we can get into the math if people want to. But, so here are some art examples we can use. So this one is counting to infinity, and it's using Muybridge's famous pictures where he discovered that horses have all of their hooves in the air while they're running. Here's another one where we take circles and make polka dot patterns out of them. And one where I'm analyzing some computer science concepts. This is something that when I was learning about OpenAI, this is what came out of my way of seeing things. And then here's one where I feel this looks like bismuth tiles, but crystallography kind of thing. But so here's one of those spirals. Here's another one of those spirals. So compiling them together and then also nesting them. So here is a whole section made up of other little spirals. It also works for 3D. So the same principle can be applied to 3D projections. So it's a little Escher-like. And then this is just actually the tip of the iceberg. There's much more possibility with this. Here's an example of something I just recently thought of, which is using that, comparing this length, comparing this length to this length down here. So instead of using 2b, using 4b, and then this allows for two separate spirals to be entangled. And another nice thing about this is that this the vanishing point is right at the center of the rectangle as opposed to off to the side. And then this can also work not just for right triangles, but all types of triangles, though it doesn't fully tile the plane. It's a bit different of a situation, but here's the traditional one that just tiles the plane. And that's it for the presentation. So here is a program I made. Please visit this, and this is what we'll be doing for the rest of the workshop. And then here is an example of using it. So here's Tardis. Just drag and drop the Tardis in. And then output it. And then here's this Tardis spiraling into infinity. So this one, the Tardis gets small very quick. So another way to do it is this way. And then the Tardis maintains a larger size for a longer period of time. And then in the settings, the difference between those two is that vertical is set to true. So the Tardis starts off vertical. And in this one, it's horizontal that it starts off on. All these things are spiraling counterclockwise just because of the way I did the coding, but that's obviously up to the user. This is automatic, so it's very simple, but the manual way to do it is I use Inkscape. And I can show you that briefly, and we can get into collaborating. So with Inkscape is a little bit more mathematical, but here's that formula I showed earlier, C minus B over A. So now we have 2/3 as the decay. So we take 2/3 and do this. So as you can see, it's a bit more labor intensive than just dragging and dropping, but also a lot more whatever you want to do. So we can speed it up by using powers. So now I do by 2/3 to the 4th, and that drops that down all the way into that spot. And so you just do powers all the way. So if I want to do even more, now I do it to the 8th. There, it fits in there. All right, well, that's pretty much it. So I think I'll leave it open to questions, and then I can tailor the workshop to what you all are interested in looking at.
I have a question. Can you hear me?
Yeah.
What made you like kind of interested in this topic?
Yeah, I got interested in this topic because I was trying to figure out a new way to write JavaScript that was a little easier than traditional methods. What I was finding was really difficult was the for loop and visualizing what was actually happening with that, especially when I had multiple for loops within a script. And so this allows me to see each iteration of the loop. So each iteration is a tile. Yeah. And then with that, I was able to think of different kinds of syntax in JavaScript. So we can get into that if we want, into the computer science aspect of this stuff. But yeah, I did that I did it for computer science.
Yeah, I'd love to get into that if no one else has any questions. That sounds really cool.
Okay. Yeah. All right. Yeah. So I'll screen share again, and then I'll open up the back end here. So let's see. Oh, the script doesn't look good in this. Here we go. Here's the script. So yeah, so here's the syntax that I developed. The syntax for a normal function, it only calls one variable. That variable is the return value of the this object for the constructor function. And then the constructor function has all of the variables within it. So I wrap, if I'm using a function that needs 8 or so variables, I wrap all 8 of those variables inside one parent object. And then I reference those variables with the parent object. See, so here, the parent object is 1. And then I reference the select input within it. But then I can go to something that's nested higher, 0 here. So 0 has lots of variables listed in it. 1 has lots of variables listed in it. And then with this allows me to not have namespace collision. So if I have a couple of variables named the same thing within multiple functions, that's okay, because within the namespace, they have different indexes depending on where they're nested within the script. And when we've got loops like this while, it becomes really, really useful. So here we see I've gone down 3 layers. So I have 0, and then 1 is nested in 0, and then 2 is nested in 1. So with 2 has access to lots of variables, actually, because within 0, within 1, within 2, there's a whole list of subvariables. And so when 2 does its loop, everything is well contained. And I can, especially if I have 2 different loops that are operating, so I've got a parent loop and then a child loop that are operating, I can keep those compartmentalized and have them work together. So this doesn't look like the tiling, but to be able to conceptualize this type of structure, which is very, very abstract. I don't know how much I got across explaining it just now. It's much easier to think about this, which is not, I mean, it's still abstract, but at least it's visual. Yeah. Are there any questions there with that? That's fairly technical, but.
So I saw there's like an event, you're adding event listeners, and are you using bubbling to like deal with the recursion? Is that what's going on? Or I'm just trying to.
For the SVGs or for the JavaScript?
I'm not sure how things are being plotted in the end, I guess.
Yeah. Oh, so I'll show you that part in the JavaScript, and the plotting isn't that great. I'm not that familiar with SVG. But I'll show you what I do. So yeah, so this script here, oh, I got a screen share. Sorry. So here's what I do. So I have animate motions that then, actually, you know what? Maybe the better way to show it is to actually just open up an SVG. So I'm going to do that.
Does the DOM represent the recursion, I guess, is what I'm also trying to figure out. Like, or is it just a bunch of flat images or clones?
Yeah, it's flat images. So here's the HTML, and then the SVG is just attached into the HTML as a nested document, but it can be saved outside of it. But yeah, so within it, then each one of the pictures is an H reference. And so then I list all the different pictures. And then I have animations that's basically like a domino effect. So yeah, so you can open up the back end and look at the mechanics if you want, but just a lot of animate motion, animate transform. And then at the end of object one, once that's done, it tells object two, okay, start. And then when object two is done, it tells object three to start. So it really is a domino style. That's how I built it. So which is recursion, but then the JavaScript function, it's a loop. So the loop prints out the SVG. The JavaScript prints out the SVG. So yeah, so the loop, how many recursions the loop does, that is this right here, repeat. So right now I have it just repeating 12 times, but it can repeat up to infinity. I mean, if the computer can handle that much raw data. And then what that will be in SVG is just a large SVG. Every repeat is tacking on more data. Does that make sense?
Yeah, that's a little clearer. Thanks.
Yeah, no worries. Yeah. And yeah, you can really get into the nitty gritty if you want to look at the JavaScript, but that's the basic concept. But again, I'm sure there's a much smoother way to do this. Yeah. Elliot, you had a question?
Yeah. I think it's cool that you've taken this math concept and translated it into code, and you've sort of found your own way of doing that translation, quite a creative way, and something that helps you conceptualize like translating the math into the code. So I wonder what your inspirations have been in terms of how you're writing this program.
Which program specifically?
Alchemy and the tiling.
Yeah. The whole reason I did this was actually for something called Twilio, a telecom service, and it's heavily event driven. So to deal with all that asynchronous randomness as well, right? Because someone just calls you at any point, you don't have any notice, right? And then who knows what happens? Maybe they connect with you, or maybe they don't. So there's many as far as the decision tree goes, it's really difficult to anticipate that beforehand. But with this setup, that doesn't matter so much because if we think about the data stack, I don't have to be too concerned if the stack is going to be really big or it's going to be really small, because with the data stack that is in a finite space and it has infinite disks that can go on top of it, then I just decide how many disks I want in that moment. It's the same amount of finite space in that rectangle, whether I use 12 disks or I use 1,000. So then I don't have to worry so much about what happens in the moment. I just know how many rectangles I need to have for whatever moments happen.
I see. Interesting. So it almost seems like you're the result of, I saw in one of your slides, you were using the tiling to visualize some programming concepts around events. So it almost seems like the way you write the code is informed by the tiling program as well as vice versa.
Completely. Yeah.
Cool.
And even my, especially nesting. Nesting is this concept that is really foreign before I got into computer science. Trees, I guess, do that branching thing, but otherwise, other than real life trees, it's not really something that we engage with. So now it's pretty easy for me to think, okay, well, I've got this rectangle, and then I made one disk in the rectangle. Well, that disk is itself a rectangle, so then that can also be an infinite set if I need it to be. So then I'm not so nervous about large numbers, because an infinite number or close to infinite is the same as just one. So definitely I don't know if other people have experienced this, but with computer science, it's really exhausting for the brain to kind of imagine all the different scenarios that can happen. With this, I'm still exhausted when I write code, but less so. There's more intuitive elements than I was able to bring to the table before.
Yeah, I really appreciate your use of creativity and visualization to make the concept more intuitive.
Thank you. And then one thing too that's fun is I do a lot of hiking. So I think about it as walking down a path, and you see the mountain really, really far away, and then you spend a day, and then suddenly you're right at the foot of it. And so playing with images that kind of have that aspect in it, because there's a vanishing point there. I've found that there's some stories I can tell, that they're not just one moment like visual art often is. There's a bit of motion that can be imbued in it, or a sense of change. So like this one, for instance, it can be subtle, but this is keep calm and spiral on. So that whole concept of, maintaining and persevering for a long period, let's say people are bombing your city and you just got to hunker down. The spiral part of it, the fact that it's repeating and ongoing, gives a sense that there's a temporality here, and one has to keep going and not stop, which, you know, the poster itself does with words, but then with this imagery, I feel like it gets a little bit more into that. Or one I made I like is a wolfhound chasing a rabbit, and it's just a still image, but even just two still images, then you can create a lot of motion with just two still images if you have the rabbit a little bit smaller in the next image. It conveys that the rabbit will never be caught. The wolfhound will always be just a little bit of ways. So I don't know if people know Zeno's paradoxes, but the arrow one, yeah, that influenced me quite a bit when I got into this. And in this scenario, the arrow doesn't ever reach the vanishing point. So yeah. So one thing I was thinking about, if people are interested in it is, since it's something that we all can kind of interact with, is thinking about a picture that would do something added value in this context. So as I just described with the spiral or the wolfhound, if you're feeling creative right now, maybe drag and drop an image or a couple images, playing around with each other that bring deeper meaning than if they were just normally tiled. And if you do have one and you'd like to share it, there's a Mural board. I'll show a link.
I have a
Mural
quick
board.
question about actually using the tool, because like, is there a specific kind of picture that works for it, or maybe my computer just doesn't want to cooperate with me today? Because like what happens when I drag and drop it, it just has the one picture and then like a square below it, and then it stops. Am I doing something wrong?
Oh no, that's great. Yeah, so then you just click on the picture, and then it'll
got
move it. Yeah.
Okay.
So it's the very beginning of the domino, and then yeah, you just push the domino.
Amazing. Okay.
Yeah. And you can change the settings so it doesn't do that and automatically starts, or that it's all tiled to begin with. Yeah.
Okay, definitely working now. Thanks.
And I just shared a link to the Mural board. So if people do want to share something on there, that'd be great. So one thing I was personally surprised about is we've known about Pythagoras' theorem for a very long time. We've known about the golden ratio for a very long time. And it's only in 1998 that Vera came up with realizing there's a generalization of this concept. And then I'm just some random person, and I've come up with even simpler generalization. So I'm still very curious about why this hasn't really been done before. And I'm wondering if anyone wants to have a discussion about that. I mean, Zeno's paradox is getting at it, right? So that we've kind of touched on these concepts in mathematics for quite a while, and information theory. But I haven't seen anywhere where people went, oh, it's the hypotenuse, this irrationality that's in the hypotenuse. We can use it in other contexts. If we just move the hypotenuse over, then that same energy can be utilized to tile a plane.
I suspect part of the question has to do with like what theoretical problem is the model solving for, like, you know, that's the thing about the way that a lot of these, you know, like a lot of this kind of work is done in like more formal settings. It's like, you know, oh yeah, there's this pattern, okay, but like what theoretical problem does this solve, right? And it's all about like, you know, like what settings, and like it's really interesting and super like really cool. I think it gives a lot of like, you know, like traction to what you're doing, that like you're like, oh, like for me this solved this problem when I was like trying to think about these like, you know, nested structures doing like JavaScript, you know, and that's like an example of the kind of thing that that makes, oh, like here's a pattern, yes, but okay, right? And what else, right? And like, what's the, what does this do for whom and what setting and so on, right? Yeah, I'd be kind of curious also to hear more about like, like what what this did for Vera, like like yeah, like you talk about the fact like like it was really crucial for her. I'd be curious to hear more about like like what she was trying to do, but with that generalization and what enabled her to do.
Yeah, and that's actually maybe one of the reasons why she's not so well known is she had a passion for it, and quite a few people have a spiritual connection to the golden ratio, and that it has a deeper meaning, and so you can find that online. That's the whole thing about the golden ratio is imbued in everything, and people get a little bit intense about it. So I think she might have been coming from that background a bit, and she wasn't able to ever put it in her architecture. There wasn't a practical use case. And other mathematicians had already known about this stuff with just pure numbers. So her moving it into imagery to me is a big deal, but it seems for a lot of professional mathematicians, they're not so concerned with that. If it can be a symbol, that's good enough for them. But it takes a lot of work to figure out how you can translate symbols into geometry. So that's not easy. But yeah, again, if it's not really appreciated and it's a lot of work, then why do it? And yeah, she couldn't really apply this kind of fractal use case in architecture. Maybe as when we have 3D printing, more 3D printing and such, we could maybe apply it to architecture. She did inspire quite a few female architects. And so there was an award a couple years ago that was run by one of the more acclaimed female architect schools in London. I can't remember the name of it right now, but in any case, the people she inspired, they still also didn't directly use the metallic means. And yeah, so you're right. I do have an actual use case, and even being able to find this stuff using Wolfram Alpha, and that has AI built into it. That was key for me to do my exploration. So with these irrational numbers, it's really hard to know what the number actually is. It's 1 point da 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 da. So it doesn't really have any meaning. Like if you find a 7 or an 18 or something like that, we all know what that is. But there are all these numbers that don't have any visual relationship, at least in my head. And so by using Wolfram Alpha then found the closed form for me. So it's like, oh, this is the square root of 17. And I went, oh, I didn't, okay. And then that slowly allowed me to figure out the arithmetic and the algebra underlying all this stuff. So one of the things I think is maybe just the tools weren't around until computers have proliferated. And then I needed to push computer technology. So this seems to be computer technology in a positive feedback loop. But otherwise, I don't really have any other explanation why something that seems so basic in geometry is only now being figured out, starting in 1998. And honestly, I don't think I would have been able to think up my stuff if Vera hadn't thought hers. I mean, it really, the moment I saw it, just my brain exploded. I went, whoa, this is what I've been looking for. Yeah. So does anyone else have any thoughts on that?
It seems like the premise of these ratios being relevant to architecture are based upon the idea that such and such a ratio looks more beautiful to people, that there is some objective aesthetics that they provide. But I've heard that question, like, for example, these very simplistic exercises where they asked you what rectangles do you like the best. So I guess I'm just kind of, I've been on the sacred geometry kind of proselytization area, but now I'm kind of walking it back so I'm just wondering if you have any insights on that.
Yeah, I mean, I personally, I definitely learned quite a bit in mathematics from sacred geometry groups that I think professional mathematicians don't want to get involved with whatsoever, or not enough at least. And so I got some key insights, but then, yeah, the generalization that occurs in those groups, that wasn't why I was there. I wasn't into trying to find a deeper spiritual meaning. I was trying to find a way to not lose my mind writing JavaScript. And so, yes, that might be an aspect as well. It's not only how quickly I can gain insights with modern calculators. That's part. But another part is that I was willing to go into certain areas of knowledge that other people wouldn't. So it seems like the sacred geometry people don't really interact with the mathematicians, and vice versa. So where people gain insights, it doesn't then move over into those other communities. So that could be an aspect of it. I mean, anything that's fractal, people think it's just folks doing way too much LSD, right? There's that bias in there. Is, oh, you're a drug head, and okay, you're not a serious academic. That could be there. I don't really know.
Yeah, I agree that for recursion, it's really great to have a visual indicator.
Yeah. So do you think you'll be using something like this to help yourself?
Well, I don't, maybe. I have my own ways of making SVG coding, so, but maybe using some similar patterns.
Gotcha. Yeah. What about anyone else? Does this help them? I mean, when I found Vera's work, I just went, this is what I've been looking for a long time. Is it this kind of stuff resonating with other people in a similar kind of way, or is it more just a interesting curiosity?
I think this is, I think it's really cool. I think translating your understanding of code into something visual is something which helps me a lot. And I think with recursion, this is definitely something which helps illustrate that in a really cool way, and the different ways things can recurse, because your program handles a lot of different, I don't know, it shows you that there's not just one type of recursion, there's different vanishing points, there's multiple vanishing points. And so in the same way, recursion has the same properties. So it's cool that your program has a visual way of seeing some of these properties. I wonder where you think this could go in the future for you, or what you want to visualize next, or that kind of thing.
Yeah. Well, I thought I was done with it for the most part, but then that more recent one I realized were the two spirals moving in, and so the vanishing point's right in the center. That came about a couple of weeks ago. Just I woke up in the middle of the night going, oh, of course, that's very simple. I can just do a whole bunch of other stuff with this extra little simplicity. And that simplicity was me applying the same kind of general pattern of recursion, just in a new kind of way. And so I think that's something that's helped me as well, as my creativity of where can recursion actually exist in reality. By doing this work, I can see it easier. I can see when something can actually nest into something else. Before that kind of imagination was really difficult for me. And Cantor's set theory, that's quite abstract. So that's really kind of the main place where you can kind of start to wrap one's head around it. But yeah, it didn't have that tactile or visual aspect that my brain needs. Yeah. But going forward, I've got a startup I'm doing, so I think I'll be really busy with that. But the startup, it will be using visuals, so hopefully it'll be eye candy for people going forward. Yeah, people really like richness of information for visuals. So, well, that's the whole point of the fractal art, and I hope that's how people will start to engage with this math, is just on the art side of things. and then it'll, be part of their subconscious, and then who knows what will come out of their consciousness by doing that. I know I definitely going to museums and just absorbing lots of art that has helped me immensely in all kinds of ways I didn't really expect. Yeah, so that's where I think I'd like to take it. But I really would love it if people start to do their own, apply their own thoughts to this. So, for instance, I came up with the keep calm spiral on, but there's all kinds of interesting concepts that can come out of using a vanishing point in this kind of modality. So obviously vanishing point is required for perspective drawing. And it kind of changed how we made art when we were able to make it so realistic with that type of mathematics. So that'd be great if people start to take this in that kind of direction. But so if there's a visual artist who's really good at vanishing points to start with, then understands what this is and make something amazing. I don't really know. But yeah. Do anyone else have thoughts of where this could maybe head beyond me as a aesthetic? I mean, I might be like Vera, where no one really paid too much attention to her the whole time with it, because she didn't really have any direct application, right? If I'm sure she made some amazing buildings that had the art as part of it, she'd be better known. But it just kind of stuck as an obscure thing on the internet, and people were interested in infinity, started to pay attention. So PBS Spacetime, the guy who used to host it, he's the person who introduced me, I mean, just on YouTube, but introduced me to Vera's work. He was in his Infinite series, PBS Infinite. Yeah. So he's a physicist, mathematician, so he was curious about this kind of stuff. And I definitely started on this because I saw Roger Penrose at a Royal Institute, and he was using tiling, aperiodic tiling. And that's what he's really focused on. So I already knew about Stephen Wolfram and his cellular automata. So I went, well, you know what? This is kind of like cellular automata. I feel like what I'm up to really at the core of it is it's aperiodic. That's what's making me so frustrated on the computer science side of things. So I'm going to explore tiles and other forms of what could be considered aperiodic. And yeah, and that's why I went on this journey. So it has been a mixture of math and physics. I'm neither a mathematician nor a physicist, so I can't bring it into those fields really. Hopefully, people in those fields will pick up on this and have amazing insights with it. I feel like eddies, maybe this could apply to eddies, but I don't know, just because they look like spirals.
Have you played around with like sound applications?
Yeah, a little bit. That's also, yeah, a very fascinating space for this. My gut as a musician thought that we were being a little bit shallow with our sense of how much wealth was in there in the visual space. Yeah, there's a rhythm, and I can come in with all kinds of sub-rhythms, and that just wasn't really there with tiling and visual art, where you can have lots of people layer on top of each other, and it actually just adds to the beauty of it. So we'll see. I do have some sequences that I figured out through this that are on the OEIS, and they've got a music system that translates it. And so some interesting music has come out of that. But a main issue with this stuff is that it's going to take some coding for people to just play with it on a fun art level. So I spent quite a bit of time for this presentation on that website, so you can just get the basic sense of how you can play with it, right? Just drag and drop the picture. But it's very limited. You can only spiral in one direction. So it's just trying to get the idea there, but hopefully code will be built on this, and then people can transpose it into music and other kinds of things, and we can see the beauty that right now my particular version isn't showing. I do think there's a lot more interesting stuff here than I have the time for. It's very, very rich. Yeah, some of the music that's come out of my sequences are surprisingly interesting. Some of them are just really basic and repetition, but some of them don't ever really repeat, but it has an underlying theme. Yeah, 1 plus the square root of 7. So these sequences I have are 1 plus square root of something or other. These OEIS sequences. They're on the GitHub if people want to look at that, but that's really, really mathy. Yeah. And maybe it could be music-y at some point, but not anytime soon. Yeah, does anyone have any other questions? Well, in that case, I guess we don't need to go to the very end. We can finish up early, unless people want to work together on something. I think I've explained what this is, and hopefully this stays with you into the future, and that you see it again when it's more developed and a little bit more user-friendly and accessible. Thank you for being with me in the early stage of this journey.
Thank you. That was a fun discussion.
Thank you.
Yeah, thanks.
Yeah. Thanks, Kyle.
Thanks, everyone, and enjoy the rest of MozFest.
Will do.
Paul?